So we discussed the RBS and the use of the RBS and how it's going to help us to dissipate the energy and control the location of the plastic hinge. So instead of having the plastic hinge at the interface between the beam to the column, now we're shifting it. We're controlling its location. We want it to happen here. We don't want it to happen in this location. We don't want it to happen in here, but we are controlling it to be right at this cut. And this cut, we call the RBS, the beam, the reduced beam section. So here it is, the RBS. Here's the meaning of it. Reduced beam section is the RBS design. Okay, good. Now we understand that once you put this RBS connection, it's going to get you a bigger hysteretic loop, if you like, or loops, and the dissipation of the energy is going to be much higher than that if you don't have it. So if you don't have this RBS connection, the hysteretic loop here is going to be kind of pinched in the middle. But if you're going to put here again the RBS, you're going to see that this is going to be kind of inflated. It's going to be like big, and it's going to be dissipating lots of energy. I'll give you some examples, and we'll discuss this protected zone thing. And we'll say protected zone usually in the RBS, and it's going to be maybe a little bit after it. So like here, if someone's asked me where is this protected zone, I'm going to say it's going to be at the interface of the column, and it's going to be for a distance of roughly, I'm going to say maybe 2D of the beam depth. So if this beam depth, let's say 27 inches, I'm expecting maybe 54 inch of protected zone. It's kind of like rule of thumb. In the eccentric brace frame, in the EBF, is going to be in the leg beam, and in the brace frame, is going to be middle quarter of the brace. So the reason that we have this braces is not related to a brace frame. It's just braces, and here's a beam, the frame beam. So this here to brace the bottom flange of the beam. Why? Because if this bottom flange at one time is going to be tension, the other time is going to be compression, you want to be sure that it's really braced at the bottom when it's exposed to compression. Otherwise, you're going to be losing the strength and the ductility of it. The other system here, which is, I'm going to say your patent system, is going to be the SSDA, the slotted web. So what they do here, they come and then they cut the web right here. They drill first a hole, and then they do this long slot, if you like. So once here you disconnect the web to the flange, you control the amount of moment that this section is going to be able to support. So the flexure capacity of the section right here, when you have full connection between the beam web and the beam flanges, of course, it's going to be completely different when you have a cut or a hole through it. So with that, the flexure capacity of the beam section, based on testing, not based on analysis, because if you like to do it based on analysis, you're going to get very close number to this cross section right here. But actually, based on testing, the flexure capacity right here at this section is going to be much less than that of that section. And with that, you're going to be controlling the location of the plastic hinge tapping at this place. I'm not sure if you guys are familiar with the ICCES, International Code Council, Evaluation Services, and they have certain reports. So I'm going to say, here's the report number. So I'm going to put it right here and say, National Code Council, or let's just say ICC, right? And this gives you the report number. So the report number in this case starts with ZSR. So you can look it up, you can download it if you are interested in it. And you see that this is not really in the code, but if you like to bring something to the code, or if you like to use it and is not listed in the code, you need to establish this ICC report. And this is exactly what this company has done. They established this ICC ESR 1093, and based on this, you should be able to use it. Within this report, you're going to see design methodology, and you're going to see maybe an example there. It's going to show you exactly how this is designed. You're going to see also some details, and look at the detail here. You have the column and the beam. You can have either weld or bolts. And you're going to have a slot in the web itself. So the shear plate is not really part of the business that you're doing, not part of this invention, I'm gonna say. But you can just connect the beam to the column to transfer vertical load through this shear tab. You're gonna have the same continuity plate. Here's a continuity plate top and bottom on both sides. You're gonna have also this Doppler plate. Just to be clear on the Doppler plate is gonna be this plate that we add here to, which is this red box, to the web of the column. Now let's look here at the RBS and how it's gonna get designed. Whether you're using 2005, 2010, or 2016, you're gonna end up with exactly the same method. There is no real change in the RBS design and procedure. Here's the RBS. We have three variables. It's called A, B, and C. A is gonna be the distance away from the face of column that you're gonna be starting this RBS. B is gonna be the length, if you like, of this RBS. So it's gonna be the length of the cut. I'm gonna call this gonna be the length of the cut. This cut here is gonna be actually a part of a circle. So if you like here to draw a big circle, I'm gonna be doing here a big circle, right? It's gonna be like part of it. It's gonna be like this. And this circle, it has a radius of R. So here's R, which is the radius of this circle. I'm gonna call it here the cut circle, if you like. So it's gonna be this distance, the amount of cut that you go through the beam flange itself. I'm gonna be calling this C, and from the other side also I'm gonna have another C. Since this is here a section of a circle, the radius can be given by the two values C and B, like in this equation here. So if you decide on the C and B and A, you can come up with this radius. And you say the radius is going to be equal to 4C squares plus B squares divided by 8C. So it's going to be a simple thing for you to do. So this radius is going to be important for fabrication. So if you like to get a steel fabricator, you want to give him A, B, and C. You also would like to give him the radius so that he can do their business. He can do the cut easily. Now, we need to have limits and range for A, B, and C. Otherwise, you can just take any beam, you're going to be start to do your business, your analysis, and then at the end of the analysis, you're going to say, yes, this A and B and C, the range was okay, or my choice was okay. So instead of start from scratch, the code here also, it gives you some limits, like a range for A and for B and for C. It says here A is going to be ranging from 50% of the beam, this says here B, which means the width of the beam flange, to 75% of the width of the beam flange. So, okay, what does it mean by that? It means that this C is going to be ranging from, again, 50%, right, of the beam flange to 75% of the beam flange. So here's the beam flange from here to there. And we're talking here about this A. So this A is going to be equal to 50% to 75% of the beam flange.
Good boy, Tank. Good boy.
All right, guys, be careful. Your microphone. So the first limit that I have here is going to be for this section A, or the distance A. The distance A is going to be that point where we're going to start to have the cut. And this distance A is going to be ranged from 50% of the beam flange to 75% of the beam flange, as it says here. You see this A is going to be between 0.5%, like 50% of the beam flange to 75% of the beam flange. And of course, you're going to pick a good number. For example, if the beam flange here, let's say, is 12 inches, what A should I pick? You can say somewhere between 6 to 9 inches. But if the beam flange is going to be, let's say, 12.6 inches, so you're going to start to say it's going to be ranging from 5.3. I'm going to say this is not a good choice. You don't take like like one of these numbers, right? You need to take a good number that's going to be good for fabrication, for construction. That's why you have a range. Now the second item here, which is B, the length of the cut, this length of the cut from this point to that point, how much this is going to be. I'm going to say also I have a range from 65% of the beam depth to 85% of the beam depth. When it says here D sub B, it means depth of the beam. In some other cases, you're going to see here D sub C, which means depth of the column. Now, where's depth of the beam? Depth of the beam is going to be this distance from here to there. Depth of the column is going to be from this point to that point, which means from here to there. So I'm going to say here's D sub C, if you like, depth of the column is going to be from this point to that point. And depth of the beam, D sub B, is going to be from here to there. So, okay. So I have here a range also for B. It goes from 65% to 85% of the beam depth. How about C? The amount of cut, this little cut that you're talking about here. So this is going to be a range of 10% of the beam flange width to 25% of the beam flange width. So I said, okay, yeah, I have some range. So whenever I have the beam dimensions or the beam size, once you decide on the beam size, what you need to do, you can come up with A, B, and C based on this range. And you should be fine. Whatever the selection that you're going to be going with is going to be fine for now. At the end of your design, you're going to confirm that your choice was good. Because again, one of the checks that you need to do is to be sure that this section is going to be the weak link, is going to be attracting the plastic hinge to happen at this location. So after you choose A, B, and C, you need to come back and confirm that this choice was a good one. So I have here the radius based on this equation, which is the same equation. So you can put here in the red box, and you know that you're going to be using it at one point. And the reason that you need to have this R is only for fabrication. So you don't need it later on for the analysis. It's just to specify to the fabricator, say the radius of the cut is going to be this much. So okay. And then it says here the plastic hinge may be assumed to occur at the center of the curved cut. I'm going to say, where's the curved cut? I'm going to say, here's the curved cut. And then it says here, there is a dimension that I'm going to be calling here S sub H. S is going to be the spacing, H is going to be the hinge. So S sub H is going to be the distance from the center of the column to the center of the RBS. How can I find this SH? I'm going to say it's going to be equal to 1/2 of the column depth plus A plus B over 2. Why is this? Because let me draw this here. Let's say this goes right to the center of the hinge. So it's going to be B over 2, this side here, plus A, plus the depth of the column divided by 2. Depth of the column divided by 2 is going to be from the center of the column to the face of the column. Okay, all right, here it is. D sub C is going to be the column depth. Now I know this, right? I know that D sub B is going to be the beam depth, but D sub C is going to be the column depth, which is the distance from this point to that point. Plus A, this is the advanced point, plus B over 2, 1/2 of B, which is the cut length. So I'm going to say this also, distance is going to be simple, and I really need distance in my analysis. So when it comes to my analysis here, I really need this. Now I want you to look at this picture here. Here's the moment frame before the formation. You see 2 columns and 2 beams. Now you start to push it with some point loads like this, right? You're going to have a point load here, another point load here. Now the frame is going to start to sway. It's going to start to move in this direction. But because I wanted the plastic hinge to happen at this location, I'm going to be expecting that the deforming shape is going to look like this, especially beyond the elastic limit. So as long as you're within the elastic limit, you're going to see this beam here to be curved. And once you get to a point, now the beam is going to start to hinge, right? And it's going to happen after the yield point. So once the beam is going to start to hinge, this is going to be kind of exaggeration when it comes to the deforming shape, as you know. Now, this angle between this little piece of the beam and this column is going to be equal to 9 degrees. So I'm going to say this angle that I'm pointing at, right? This angle between the beam, between the frame beam and the frame column is going to be equal to 9 degrees. This also is going to be 90, 90, 90. Same here, 90, 90, and 90, and 90. Therefore, the distance from the plastic hinge to the plastic hinge is going to be equal to the center to center span, the center line to center line span, which is here called L sub 0. So we can say center to center span is going to be called L sub 0. And then you subtract 2 times S sub h. Here's S sub h from here to there. You can say, yeah, it is written right there. It's called L prime. And L prime is going to be from hinge to hinge location. It's going to be equal to the total span, center to center span, subtracting 2 times S sub h. Does everybody follow me? Any questions?
All good, Professor.
Okay. All right, very good. So what's the importance of this? Now, when you push the moment frame to a certain point, you're going to be developing here the plastic moment. What is a plastic moment? Plastic moment is going to be equal to F sub y times Zx. So we can say here, what's the definition of the plastic moment? Just so you guys know, M sub P equals to Z sub x times F sub y. So actually, if you take this plastic moment multiplied by the phi factor, the point line that you're used to, is going to be the moment capacity of the section, phi n, if the top flange, like let's say that you have possible moment, right? If the top flange is fully braced. So phi n is going to be equal to M sub P multiplied by phi, which means M sub P is going to be the same as M sub n. So you can say it's going to be the same as M sub n. There's no big difference, unless you have buckling issue within the beam. So in this case, M sub P is going to stay as this number, and M sub n is going to be slightly lower. So we can say this is true if flanges are braced. So when the flanges are braced, M sub n is going to be the same as M sub P. Once it starts here to have some buckling in the compression flange, M sub n is going to be lower than M sub P. And we know this from the beam design a long time ago. So now I understand M sub P. So at this point here, M sub P is going to start to form. But we have an issue here because the actual F sub y is not going to be equal to the specified F sub y. So what's the specified? What is the actual? I'm going to take you back here to, I don't know if you have it here. No, actually I have the previous slide set. R sub y and R sub t. What is that about? This is going to be for the yield strength. So we're going to say the expected yield strength for a steel beam of 992 or 572 is going to be 10% higher than the yield strength. Meaning, if you like to use F sub y in the seismic analysis, in that sense, you need to take F sub y of 50 ksi multiplied by 1.1. So the expected is going to be equal to this, R sub y multiplied by F sub y. So, okay, what does it mean? It means when you do your analysis here for M sub P, you need to multiply by R sub y. You're going to have a 10%, additional 10%. Because now you'd like to know exactly where the section is going to yield. This is what you're going to be interested in. If I may take you back to this performance curve, if you like. Performance curve for the seismic members or seismic frames. I'm expecting something like this. You'd like to figure out how much is this in terms of moment, in terms of force, right? So this actually is going to be based on the yield strength. So when the actual yield strength is going to be 10% higher than the specified, you need to take this into account because you know that the hinge is not going to happen at F sub y. It's going to happen at a higher value. It's going to be happening with this red line because of this additional 10%. So this is the reason that you need to account for it. Okay. I understand that M sub P is not going to get developed. It's going to be slightly higher value because the expected yield strength is going to be higher than the specified. This M sub P is based on the specified, just F sub y. Now, R sub y needs to be in the picture. So I'm going to say, okay. So instead of having just M sub P, I'm going to have here M, the probable plastic moment. So we have here a difference between the plastic moment and the probable plastic moment. Probable plastic moment, as you see here, F sub y multiplied by R sub y. I'm gonna say, okay, now I understand this. How about this Z sub E? I'm gonna say Z sub E is like the same as Z sub X. So I'm gonna take this to be Z sub X. Now I see a new term here introduced. It says here, estimation of maximum connection strength expected. Well, that's strain hardening. You know, when it comes to steel stress strain relationship, I have here two factors, right? I have the yield point and also I have the strain hardening point. You put this here. So I'm gonna say, my understanding is, actually yield point is gonna be slightly higher than this point. So it's gonna be coming to here. So I'm gonna draw here a line. This addition is gonna be like 10%. Why? Because R sub y is gonna be also equals to 10%. But you know, when you are gonna be going here in the post-yield performance, you cannot really confirm that the stress strain that you're gonna have within the steel beam is gonna be within this only this range. And most likely it's gonna be going through the strain hardening, which means this point also is gonna be slightly higher. It's gonna be more. It's gonna be like this. And if I like to develop here an idealized performance, I'm gonna come here and do it this way. Which means it is not just about the increase because the specified versus the actual or probable. It's gonna be also because the strain hardening. This is the reason I'm gonna have here additional factor, which is this CPR. So this CPR is gonna account for the strain hardening, and R sub y is gonna account for the actual yield strength. So I'm gonna have here two factors, two multipliers. One of them is gonna be called here R sub y, and the other one is gonna be CPR. Now someone's gonna say, now how can you come up with this CPR? I'm gonna say, look at this. What's the CPR about? CPR is about the yield strength, which is this point, this value, versus the ultimate strength. It's gonna be somewhere here in between. So the code here gives an equation. Says, take this CPR to be equal to F sub y, the yield strength, plus the ultimate strength divided by 2 times F sub y. And they say it needs to be within 1.2%, 1.2 only, not more. Meaning, if you run your analysis and this value turned to be 1.4, just use 1.2. Understand maybe that you're gonna have a bigger effect from the strain hardening, but the code here limits this factor to 1.2. So in this case, I'm gonna say roughly, you're gonna have here 1.2 multiplied by 1.1. And this is gonna be an increased factor to account for what? Again, it's gonna be for the actual yield strength, which is a probable yield strength, and also to account for the strain hardening. As you guys know, this is gonna be our idealized yield stress-strain relationship, because it's gonna be really tough to use this stress-strain relationship when it comes to analysis and design. I'm not gonna be able to do this. So instead of this, I'm gonna come up here with some curve, which is gonna be kind of idealization to the actual stress-strain relationship. So okay, it's gonna be MPR. Now, when do you think this MPR is gonna get developed? So I'm gonna say, okay, hold on, let's put this aside and let's open a new topic that I want you guys to know about. Let me put it there, which is gonna be plastic analysis of moment rings. We need to understand maybe just one example to open this road for us. Otherwise, it's gonna be kind of real tough. I didn't post this yet. I'm gonna post it right after the lecture. It's gonna be a complete set here. It's only 10 slides, but it should be very useful after this. So I'm gonna say here, we have something that you call sway mechanism. What's the sway mechanism? In the sway mechanism, you take here a moment frame. Let's say that you take this moment frame. You start to push it. So, okay, we're gonna start here to push it. This frame is hinged or pinned at the bottom. This is gonna be moved by amount of delta. And don't forget that this beam here is connected to a rigid diaphragm. So you don't have any problem in bending of this beam. You just push the entire frame this way. So the amount of drift that you're going to have in the first column is going to be the same as the amount of drift that you're going to have in the second column. This absolutely makes sense. You push it here, this point is going to be moved by delta. This also point is going to be moved by the same amount, which is delta. Now, since the column height is going to be the same, which is h, I'm going to have here an angle of rotation. And usually, if I say the angle of rotation is going to be in radians, because I'm not trying here to find out the sine of this angle, any of this trigonometric functions. I'd like just use the angle as is. So I need to use it as in radius and not in degrees. Now we're going to start to push the moment frame, and then push it more and more to a certain point. Once the column is going to be forming a hinge right at this location. I'm going to say here, hinge location in the column is going to be right here. And also hinge location in this column, because these two columns are identical columns. I'm going to be also forming another hinge right here in this location. And at this location here, I'm going to be developing the plastic moment M sub P. So what's M sub P? M sub P, again, if you look at the previous slide set, the way that I put it there, before I added the C sub R, and before I add the R sub Y, right? I'm going to say M sub P equals ZX times Fy. So, okay. So when this moment is going to get developed, what's going to happen? Two hinges going to form here, and the entire moment frame is going to be collapsing because there is no resistance for it. Now, look here at the lateral force displacement and the stress-strain relationship of this idealized system. It means once you reach here the yield point, what's going to happen? You're going to have excessive deformation and no resistance, because there is no resistance here for this. I mean, the stress is not going to be going up. There is no resistance here for the entire lateral system. This is why we call this mechanism. So what does mean by mechanism? Mechanism means that you're going to be forming hinges, and after that, the entire system is going to be collapsing with any additional load. So we can say, how about a mechanism for a simply supported beam? So let me put here this simply supported beam, right? I'm gonna put here two supports, one support here, right? Like a roller, and the other one's gonna be like a hinge. I'm gonna be applying here a point load right in the mid span, if you like. It's gonna be like this. What is a potential mechanism? So I'm gonna say mechanism means failure. Where's the failure is gonna happen? I'm gonna say you're gonna keep on pushing this beam down, and the moment diagram is gonna be maxed out at the middle of the beam, right? The moment diagram is gonna look like this. And the more you increase the value of this load, the more deflection is gonna happen, and the moment is gonna get higher till it hits M sub P at this location. And right away, a hinge is gonna be formed right at the mid of the span, because it's gonna be the point of the maximum moment. We call this now that this beam is gonna start to produce a mechanism. Now, are we clear on the term mechanism and what is the meaning of the mechanism for everyone here? Yes?
Yes.
Any questions on the mechanism concept? What does it mean by mechanism? Let me repeat it here for quick. You're going to be adding this point load to the beam. You're going to start to push down, and the moment is going to be increased till you hit M sub P of this given beam section. Now, someone's going to say again, where is this M sub P? How can I find out M sub P as a value? It's going to be like a limit. I'm going to say here it is. Here's M sub P. M sub P is going to be equal to Zx times Fy. It means that we are reaching here the yield point, right? And the beam is going to start to go into this inelastic response or behavior, if you like. This can happen in this beam and also can happen in this frame. After this, just the frame is going to be drifting. It's going to be collapsing, because that's what you call here mechanism. Same thing with the beam. Once the hinge is going to be formed here, what's going to happen after this? Now you start to add more load. What's going to happen? There is no resistance, and the beam is going to be just collapsing, because if you have this beam and then you're going to have your three hinges, it's going to be unstable. Look at number of equations in this case. Number of equations is going to be, here is, you have the main three, and then you have also a hinge here. It's going to be 4 equations. and you have only 3, let's say, reactions, 3 unknowns, right? So when you have 4 versus 3, it means that you have unstable system. Same thing here in this moment frame. This moment frame, it has 4, right? 4 reactions. You remember we have here 1 reaction, 2, 3, and 4. You have here 4 reactions, 4 unknowns. Now, how about equations? We have 3. Now, all of a sudden, you're adding 2 equations to it because of the hinges. What is that equation? The moment at this hinge for one side of the moment frame when you cut the section here is going to be equal to 0. Same thing here. What does it mean by adding one more equation? When you have a hinge, it means when you take the moment right here at the hinge for one side of this beam is going to be equal to 0. So in here now we have 5 equations, and then we have 4 unknowns. It's going to be unstable system. So this table here is going to start to form a mechanism. Now, I want here to cut a section and assume that now we are going to be in the mechanism. So the moment here is going to be equal to how much? It's going to be constant. It's going to be equal to m sub p, correct? You say, okay, now moment's going to be equal to m sub p. Now, I'm going to have a reaction coming this way. So what I'm trying to do is to take the moment only for this section of the moment frame. I'm going to say it's going to be equal to 0 because I formed the mechanism. So take the moment here. You say, okay, let me take the moment. I'm going to say m sub p equals. Now this force, you can call it R. So I'm going to call it here this R. It's going to be the reaction, right? This horizontal reaction. So it's going to be equal to R times what? Can someone help me? R times
Height of the column.
height of the column, H. How about here? Can I do the same thing here? I'm going to say yes. You can do the same thing. And if these two columns going to be identical, this R is going to be equal to 1/2 of this F. Understand that? So I said, okay, this is good. Also, I can do it with some energy calculations, which we're going to be doing later on. If you like to do here the energy analysis, what you need to do is to set the external work, which is energy, is going to be equal to the internal work. So what is the external work? You have a force here pushing the entire system for a distance of delta. So the external work is going to be equal to F times delta, right? And the internal work is going to be equal to MP multiplied by the rotation, which is the theta. So you can set the external work is going to be equal to the internal work, right? This famous equation that you guys learned in the past. And based on this, you can come up with the force. You're going to see the force, which is 2 times this R because you have 2 identical columns. So you can say here that R is going to be equal to 1/2 of this. It's going to be equal to MP over H. And this is true because MP is going to be equal to R times H from our simple equation. So whether you do it with the structure analysis method, like to simplify it this way, with the way that we just cut a section and we have taken the moment, or if you like to go through this energy calculation, you're going to end up with exactly the same results. Are you guys good about the mechanism and the developed force here? Yes?
Yes.
Okay. I said, okay, good. How about if I have a column fixed in the top, fixed at the bottom? It's going to be for the same column because the column section is going to be the same. I'm going to say it like this. What's going to happen here? I'm going to say you're going to be pushing the frame. The frame is going to be drifting. At one point, it's going to be hinging top and bottom at the same time. So you develop here M sub P and M sub P. Now, how much is this force? If I'd like here to take the moment about this section, I'm going to say, let me take the moment about this section right here. This could be my section. Right? What can I do in this case? We're going to say, okay, let me take the moment. For only this section, I'm going to have MP plus MP. So I'm going to have 2 MPs, right? Equals to what? It's going to be equal to some horizontal force. I'm going to say in this case, I'm going to have horizontal force coming this way, which is the same as the horizontal force coming this way in the column only, right? Which is 1/2 of F, right? So I'm going to say 2 times MP, because you cut the section, you take the moment here. 2 times MP is going to be equal to the force R, which is a reaction, times H. So these two forces within the column only, not the F. It's gonna be only the force within the column, which is this R, right? The reaction. This is gonna be like a couple. It has a distance of h between them. In this moment, the rotational moment, applied rotational moment, which is mp times 2, is gonna be equal to r times h, like a couple. So you have mp plus mp is rotating this way, and r times h rotating the other direction. They're gonna be equal to each other to provide the balance. So we're gonna say, in this case, I'm gonna be interested in r. And how much is this r? R is gonna be equal to the following. I'm gonna say it's gonna be equal to 2 times mp divided by, can someone help me here? Yes? Anyone help? H. All right, is this R represents like an axial column load or shear in the column itself?
Shear.
Okay, so I'm gonna say this R, I'm gonna call it shear. What should I call it? Column shear? Say yes, it's gonna be column shear. Do you have another name for it? And please be careful about these names because I want you to memorize them. It's gonna be also called or mechanism shear. So what's the mechanism shear? It's gonna be a shear that you develop in the structural member, and in this case, that was a column. And our moment frame in the RBS is gonna be what? It's gonna be the beam. Because look at this, the difference between this system and between my system that I'm gonna be working on. Look at this. The hinging is gonna be happening within the beam. Here, the hinges that I'm talking about is gonna be happening with the column. Two different examples, but it's the same concept. That once you start here to develop 2 MPs, you're gonna be also developing some shear with it. And we're really concerned about this shear because we don't care about the moment. It's good. I mean, when you have some moment like this, right? And you know the distance between the two hinges. Now, where's the first hinge in this case? I'm gonna say the first hinge is gonna be right here at support. Second hinge, I'm gonna say it's gonna be right here at support. So actually, this mechanism shear is gonna be equal to summation of all the moments that you develop within this structure member divided by the distance from center of hinge to center of hinge. Now let's take this applied here. Where's center of hinge? Gonna say center of hinge is gonna be here. How about the center of hinge? It's gonna be here. And the distance between the two center of hinges is gonna be equal to L prime. Now I guess now I understand why L prime is gonna be important. I really need this L prime. This is why S sub H is gonna be critical value. So the choice of A and B is gonna be controlling the distance from center of hinge to center of hinge. You see this S sub H? You have the total beam span, which means center to center span for the moment frame, right? You have this L sub 0. But you're really interested in this L prime. Again, what's the reason for this? The reason is because you'd like to figure out the distance from a hinge to a hinge. Now, what's going to happen after? I'm going to say at each one of these plastic hinges, you're going to be developing this MPR. What is MPR again? Here is MPR, the probable moment. Which problem? I'm going to say the probable plastic moment. This MP only is going to be the plastic moment. This MPR is going to be the probable moment, including the C sub PR and the R sub Y. Again, what's R sub Y? It's going to be a factor to account for the actual yield strength versus the specified yield strength. And what is C sub PR? It's going to be a factor to account for the strain hardening. I was going to say, okay, I forgot all about that. Let me put it back again. What's the strain hardening? Strain hardening is going to be that thing. It is not just that point. This point here is strain hardening is going to start. So the strain hardening is going to be that thing that after you're going to be going through the yield plateau, now the material is going to start to pick up some stress. It's going to start to get strong back again. It's going to start to come back to life. So we call this a strain hardening. So C sub PR to account for this fact that at a certain point the steel is going to be taking some force again. And R sub Y is going to account for that factor of what? Of the actual yield strength compared to the specified yield strength. So we know the specified is going to be, let's say, 50. But reality, most likely, is going to be 55. It's going to be up to here. So from that point to this point, it's going to be 10%. From this point to this point, let's say it's going to be maybe additional 20%, which is this C sub PR. So now I understand why this NPR. What should I do after I have this NPR? NPR is going to be the probable. After this, I need to find out the mechanism shear. What's the mechanism shear? I'm going to say mechanism shear is going to be this V prime at the RPS. So I'm going to say the center of the RPS is going to be right here. You see this location? Yeah. And the center of the RPS on the other side is going to be right this and this location. The distance between them is going to be called L prime. What's L prime? Let me take you back. I'm going to say here, what is L prime? L prime is going to be the distance from a plastic hinge to a plastic hinge. It's going to be smaller than L sub 0. NPR that you're going to be developing here is going to be NPR of the reduced section. Now let me take you back here. Someone's going to say, how can I find here NPR? I'm going to say it's going to be equal to, I'm going to put it here, NPR. I'd like your help here with me. NPR is going to be equal to what? C sub PR times?
RY.
LY?
RY.
RY. Thank you. Yes, times?
FY times ZE.
ZX.
Yeah, sorry.
Yeah, ZX. What is ZX? Is going to be the section modulus, plastic section modulus for the section right here. So what is this related to? It's related to that section. But you know what? When this beam is going to start to hinge, it's going to start to hinge right at this location, right? So also I'd like to find out NPR of the RBS, not NPR of the beam, because NPR of the beam is different from NPR of the RBS. The reason? Because this is a reduced section and the beam flange is different. So Z sub X is going to get reduced by how much? Yes, okay, let me call here. I'm going to say NPR for this location is going to be equal to CPR times R sub Y times F sub Y times ZE. What is ZE? ZE is going to be a reduced form of ZX because you take here the flange and then you cut a piece of it. And how much is this piece? I'm going to say the piece is going to be equal to the C from each side in 4 locations, top and bottom flange, right and left. So, okay. Let me look here at this. It says here Z sub E. Now, what is Z sub E? Now, I need to put them all together. I'm going to say, let me take this. I'm going to be taking this and this and copy it here, right? For me to follow up, right, with this. You say, what is this? This NPR is for the entire section of the moment frame. This is going to be for the beam, and this one is going to be for what? For the RBS. So this is going to be NPR for the RBS, and this is going to be NPR for the rest of the beam, where the beam is not touched yet, that you didn't cut anything of it. So this ZE is going to be equal to ZXB. Why do we call it here XB? I understand this is going to be ZX, right? By what would you call it B? What is this B for? Can someone help me here for this?
The beam?
Yeah, beam for the beam, right? Just define this going to be for the beam, not for the column. Do you want to be sure that you know which one we are talking about? I understand. If I'm going to be asking anyone here, they're going to say, yeah, we understand that this is going to be for the beam, and it's going to be ZX of the beam. So the code would add this letter B here to indicate that this is going to be for the beam, like confirmation. Now, this ZE is going to be also called Z of the RBS. Now, it makes sense that I can call this also Z of the RBX, right? RBS, excuse me. So what is Z of the RBS? Is going to be the section modulus for the cut section, for the reduced section. It's going to be equal to ZX for the beam, which is the same as this ZX. Then you subtract 2 times C. How much is this C? C is going to be the cut. You know, it's going to be this cut that you're talking about. It's going to be this little cut. So it's going to be 2 times C, right? Times the flange thickness. You see this TB is going to be the flange thickness of the beam. TF, my understanding, TF for any given section is going to be the flange thickness of the beam times DB, depth of the beam, subtracting TBF, the thickness of the flange of the beam, to get you here Z over BS. Okay. So what do you do after this? You find out NPR of where. So this NPR is going to be at the RBS. So this is why it says the plastic moment, probable plastic moment at the center of the RBS. This is not the plastic section modulus of the entire beam. This is going to be for the RBS itself. So if you like you to think about the mechanism, you know that at this point, you're going to be developing this MPR. And this MPR is going to be equal to what? If I'd like to retype it again, we can say this MPR at the RBS is going to be equal to C sub PR times R sub Y times F sub Y times ZE. What is ZE? You can also call the Z of the RBS. Now, where does this moment happen? This moment is going to happen only here and here. The plastic moment. And this plastic moment is going to be smaller than the plastic moment for the rest of the beam. Why? Because this piece here, we have a small cut. This C, top and bottom, and both sides, right and left. So I'm expecting MPR here is going to be smaller than MPR for the rest of the beam. This is why the plastic hinge is going to happen here before any other location. So, okay, great. Now let's see here the mechanism shear, which is very critical. And this is going to be the critical part in our design. How can you figure out this mechanism shear? Mechanism shear here is called V prime of the RBS. I understand that I'm going to have here MPR, and here's going to be MPR, where at the plastic hinge is going to be the center of the RBS. And this distance L prime is going to be the distance from the RBS to the RBS. So, okay. How about dead load? Do we have dead load on live load? I'm going to say yes. You may have also some uniform load. And of course, I need to use here the load combinations. If you remember the load combinations, I have one of this load combination when you have a dead load on live load and earthquake. You have this 1.2 dead plus 0.5 live plus earthquake. So I'm going to write it down here. I'm going to say this is going to be the same as ultimate load equals 1.2 dead plus 0.5 live load. If you remember the factor F1, if you remember this factor, if anyone remembers this, plus E. We have load combination like that. Exact load combination. I'm going to apply it here. It says V of the RPS is going to be equal to what? 1.2 times V of dead load. How do you do here V of dead load? You say V of dead load is going to be equal to this uniform dead load times L prime over 2. As if you have here simply supported beam. So I'm going to say this is not simply supported beam. This is a mount frame and it has continuation. I'm going to say yes, but once you have this mechanism, you're going to start here to have a simply supported structure. So I'm going to say, what is this? How much is this V dead load? V dead load equals W dead load times the L prime divided by 2. How about V life load? I'm going to say it's going to be the same. So let me write it here. I'm going to say V dead load equals W dead load times L prime over 2. Same thing for the W life load. So what is this VPR? VPR is going to be actually the mechanism shear. So I'm going to say this VPR, this is what we call here mechanism shear. Now, what is the mechanism shear in this case? Let's say mechanism shear equals. It's going to be equal 2 times MPR divided by the span. Let's say, yeah, I have seen this before, and here it is. I'm going to put it back again here for you guys. Here's the frame column that we have used for the plastic analysis mode frames. We said that the shear in the column is going to be equal to MP plus MP divided by the distance from the hinge to the hinge, H. How about here in this case? You say the mechanism shear, which is also this value, right? VPR, which is the seismic component, is going to be equal to 2 times MPR. Where is this coming from? We're going to say, let's take the moment about this point here. We have MPR plus MPR, right? Equals VPR times L prime. So we're going to say 2 MPR, when you take the moment, you're going to have 2 moments going in the same direction, which in this case is going to be what? counterclockwise is going to be equal to VPR multiplied by the spacing from the two hinges, the L prime. And for that, I should be able to figure out the mechanism shear. Are you guys okay?
Yes, sir.
Yes? Okay. Here's what's going to happen in your exam, because I need to give you this in an exam, right? At one point. In the exam, you should not expect that I'm going to give you a complete moment frame for you to design from scratch. So from time to time, I'm going to be doing some analysis on my own and give you some numbers. And then all of a sudden, I'm going to be asking you, how much is this? Let's say, for example, the mechanism shear. So in this case, if I'm going to be choosing this A and B and C for you, because I cannot let everyone just pick and choose the A value and the B value and the C value in his exam. I'd better have a choice and give it to you. Otherwise, I'm going to have 26 different solutions, right? So I should pick A and B and C. Maybe I can ask you to check if this is okay code-wise, which means that you need to look at the AI peg, compare it with the flange width. If it's going to be within this range, you say, yeah, satisfy the code. Otherwise, you say, no, this is not good. It's going to be one thing that I may ask you about. Also, I may ask you to find out R, which is the radius of the cut. Also, I can ask you to find this edge. And if you find this edge, you can find L prime. Now, also from the book, right, you have ZXB, then you have the flange thickness, you have the amount of cut, you can find out Z of the RBS. And then after that, you should be able to find out MPR, the probable moment at the plastic hinge, using the ZE or Z RBS. What do you do after this? I can ask you for the mechanism shear, which means I may not ask you here to come up with the beam size. I'm going to give you the beam size. I cannot let you check or choose the beam size. Otherwise, again, I'm going to have 26 different solutions easily. Everyone's going to say, yeah, I like this beam size. What's wrong with it? And you cannot argue, right? It's going to be okay. I mean, you have lots of designs. All of them are going to be okay. So instead of doing this, I'm going to give you the beam size, and also I can give you A, B, and C, which is the RBS parameters, if you like. Now, after this, I'd like to find out the shear at the RBS. Shear at the RBS is going to be equal to the mechanism shear plus V dead load plus V life load. Now, we need to think here. Where is the first VPR? I'm going to say the first VPR, which is this mechanism, is going to be coming up, right? The second one is going to be coming down. It's going to be an issue because at one point, this mechanism shear is going to be additive to the shear coming from dead load and live load source. The other side is going to be subtractive because at one point it's going to be going with direction of the dead load and live load, and the other side is going to be going against it. So I'm going to say in this case, I may have plus and minus when it comes to the mechanism shear. Why? Because mechanism shear can change the direction. It can be going up or going down. This is why I have it once as positive, the other one is going to be as negative. This is why they say here, this when the V prime RBS is going to be negative sense or positive sense, depends on the direction of your analysis. Whether you'd like to consider the earthquake force to be acting this way or the earthquake force to be acting this way. Because at one point, MPR is going to be coming this way, producing tension at the top. Once you change the direction of the earthquake, it's going to be coming the other direction. So the thing is, when it comes to earthquake forces, it can be coming from east or west. It can be coming either direction. So whatever that you consider here to be tension at the top, in a second, it can be also tension in the bottom, right? It can change direction. Again, this is the reason when it comes to the shear, I can have here a positive or negative value because this mechanism shear can be at one point additive, the other point is going to be subtractive from direction of the dead load and live load. Is that okay? Now, I guess I was able to figure out how much shear I'm going to have at the hinge. So I'm going to have here some shear at the hinge. I'd like to figure out how about the moment that I'm going to have here at the face of the column. How is it going to look like? I'm going to say, you know what? Let's take here this This is gonna be the RBS location, and this is gonna be the V sub U location. I'm gonna put it right there. I'm gonna say, let's say the shear is gonna be coming down like this, right? Now, how much is the moment is gonna be at the face of the column so that I'm gonna be sure that nothing is gonna happen? I'm gonna say I need this distance, right? From here to there. I'm gonna say the moment at the face of the column, which is called here MF. So what is MF? MF is gonna be the moment at the face of the column. It's gonna be equal to this vertical load, right? Multiplied by the distance. This is gonna be okay as an equation if the moment here is gonna be equal to 0. But this moment right here at this location is gonna be equal to what? To MPR. Because you know when you start to push the moment frame, it's gonna be reaching MPR, and after that it's gonna be forming a hinge, which means it is not a real hinge. A real hinge is gonna have a 0 moment at it. But our hinge here is gonna have a moment of MPR at it. This makes sense? So the regular hinge, let's say if you have any hinge, right, in a beam or a moment frame or on a column, the standard hinge is gonna have a 0 moment at it. Now this plastic hinge is different because the moment at the plastic hinge is gonna be equal to MPR. Because what's gonna happen when you push the moment frame is gonna be forming a hinge. And what's gonna happen after this? Mechanism is gonna start to fall, and the frame or the moment or the beam is gonna start to collapse. It's gonna take you back to here. You say, look at this. You don't really have a hinge. If you look at this from a structural point of view, this is not a real hinge. What's gonna happen? You're gonna start to push and push and push down, and the moment is gonna be reaching MPR of this beam, and after that it's gonna be forming a hinge. So the moment at this point is not equal to 0. The moment at this point is gonna be equal to a set value. Whether you change the load, this value is not gonna change, and this value is gonna be called MPR. This is why we call plastic hinge, not just a hinge. And they go back here and say, in this case, the moment at the face is gonna be coming from 2 components. The first component is gonna be the MPR. Second component is gonna be equal to the shear multiplied by the SH. What is the SH? We gonna say distance from the center of the hinge all the way to the face of support. So what is SH here? In this section of the analysis, it's gonna be A plus 1/2 of B, right? I say, okay, let me take you back here, because it's kind of confusing. I'm gonna say, how about SH here? What was the definition of SH? It is not really A plus B over 2 because it goes to the center of the column. Look at this. You see this SH definition? It goes from the center of the column to the center of the plastic hinge at one point. Now, all of a sudden, they change the definition of SH. Now, SH equals, if you look here, is going to be equal to A plus B over 2. You just change the definition of SH in the same code. So at one point, when you're trying to find out the distance from a plastic hinge to a plastic hinge, you say S sub H is going to be the distance from here, from the center of the column, to the plastic hinge location. Now they make it to the face of the column. So I don't want you guys to be confused. So some people will start to develop and say, I'm going to call this SH prime, for example. If you like it this way, do it. For me, I keep it SH. It depends on the location where I use it. Does this make sense?
Yes.
Yes. So everybody now understand what I'm talking about? This SH, at one point, SH is going to be to the center of the column, but in here, find out the moment at the face of the column, you're going to do it to the face of the column. Okay. Now I have the moment at the face of the column. This moment is going to be on the beam itself. Also, I'm going to have some gravity moment, and this gravity moment is going to be coming from this little cantilever. If you like, consider this to be cantilever, this is fine. And the moment in any cantilever equals to W squared divided by 2. So let me put this equation here. I'm going to say, if I have any cantilever, right? And the length of this cantilever is going to be L. Moment equals uniform load on the top, M equals W, L squared, divide by 8. To be sure that this is squared, I'm gonna do this. I'm gonna say instead of divide by 8, it's gonna be divided by 2. It says here W times SH, and in this case, SH is gonna be this distance, right? This is gonna be S sub H, which is from here to there, right? So you take this as a small cantilever, and then you load it with the ultimate load. Ultimate load here is gonna be based on this load combination 1.2 dead plus 0.5 live. Let's say this here is gonna be based on the same load combination that we have just used. So you can say 1.2 dead plus 0.5 live load. With that you have W ultimate, you say times SH squared, the cantilever length is squared divided by 2. You wanted this gonna be one of the checks. You wanted this to be extremely small compared to the moment at the face coming from the seismic. So you don't want to have lots of gravity load on the moment frame. This is what it says, right? You like to have it controlled more well, right? The mechanism shear and mechanism moment, if you like. Okay. Now, I need to figure out the expected plastic hinge or expected plastic moment of the beam itself, which we have done already. I'm talking about this one here, NPR of the beam. What is NPR of the beam? Yeah, it's gonna be based on ZX, because the one that we have just done here, that was for the RBS section, so the reduced section. But in here, it's gonna be MPE. So instead of calling it NPR, I'm gonna call it here MPE, right? CPR is not gonna be there. I'm gonna be taking it out. It's gonna be equal to ZXB of the beam itself times R sub Y times Fy of the beam. It's provided that you may change the yield strength from a beam to a column, but most likely it's not gonna happen. I'm gonna be saying why C sub PR is not there. Why didn't I see it here? I'm gonna say this kind of a safety. So the code actually is trying to make it hard on us, because when it comes to the section that you're gonna have the plastic hinge at, you included this C sub PR to add more mechanism shear. Because don't forget, mechanism shear is gonna be very critical, and then later on we're gonna be checking the beam for the shear strength. And in many cases, you're gonna have trouble with this mechanism shear. So the problem is not gonna be the moment. Usually in moment frames, it's not gonna be the moment value. It's gonna be the amount of shear that you put to the system. So it is true that you can go here with larger moment frame beam. Now you start to push it. Then all of a sudden you're developing lots of shear forces in the system. So when it comes to the moment, it's gonna be okay, because what's gonna happen to the performance curve, instead of reaching, let's say, to a certain moment, it's gonna be going slightly higher. It's not gonna be a big deal. The problem is gonna be the shear that goes with it. That once you start here to form this mechanism in the beams, at that point you're gonna be also developing shear within the entire system, within the frame beam and the frame column. And this shear is gonna be so critical that in many cases you need to reduce the beam size or go to a shallower beam just to avoid the high strength of the beam and the shear that you develop in there in the mechanism. It's gonna be just too high for the beam to be able to take it. Now, you need to check here the moment at the face of the column with the plastic moment of the beam itself. What does it mean by that? This MPE that you just determined is gonna be for the rest of the beam, not for the plastic hinge, which is gonna be in this case the capacity. So this M at the face, right? You want to be sure that this M at the face is gonna be lower than this phi Mn. What's now phi Mn? Phi Mn is gonna be based on this equation here. You want to be sure it's gonna be less than 1, which means now you'd like to limit the moment at the face of the column to be lower than phi MPE. What's MPE again? MPE is gonna be the strength of the beam itself, not including CPR. So this is the reason I said when they take your CPR out of this equation, they made it tough on us, because this moment at the face, it can be high. And don't forget, this M at the face is going to be actually based on the mechanism shear. And mechanism shear includes in there the C sub PR. So CPR, when you include it there, it is adding 20%, right, to the moment. which means this M phase is going to be including CPR, which means it's going to be higher than what you should expect. Now, when it comes to the capacity of the section at the face of the column, you see here CPR is not included because it's just taken off this equation. Also, what phi factor would I use? This is going to be a question, right? You're adding here also a phi factor for me. Now, you don't have to worry about this because phi factor is going to be equal to 1. What is the reason of this? Because use the probable. Use CPR. So don't forget that this MF includes what? Includes two big factors. Yes, this includes R sub Y and CPR. Both of these two factors. So both of these two factors is just bringing this moment at the face to be real high. So when you compare it to the strength, right now, is which strength you're going to be doing? Do you want to include also here a phi factor of 0.9? I'm going to say no. Why? Because this is going to be based on the actual performance of the beam. Also, this M sub PE is going to be based on R sub Y only, right? It includes R sub Y only. Look at this equation, only R sub Y. CPR is not taken there, which makes it tough to be able to make this work, right? And these two values usually is going to be very close to each other. So this is why maybe after you're done with your design, and once you come here to this location, you see that this condition is not working. So what you need to do is to go back to A and B and C and play a little bit with them to make this work. It's going to be here a kind of conceptual questions going to be coming to you in your exam. What's going to happen if this is not working? Which would you like to change? Is going to be the A or the B or the C? Which one do you think when you bring it down is going to bring this factor up? Which means if you have trouble here and your moment frame is not working, I'm going to take you back here. Would you increase A or reduce A? How about L prime? This L prime. Do you want to be large or do you want to be small? What happens when this L prime is going to get shorter? So let's say someone here is going to come and set A is going to be equal, let's say, to 6 inches. Another person, like a designer or an engineer, is going to make it as a foot. So someone used a smaller A, the other one used larger A. Which one do you think, which one of these two people is going to have a hard time to make his moment frame to work? Potentially. The one with a smaller A or the one with bigger A? Meaning, if I have here the choice, should I bring the two plastic hinges close to each other or further away from each other? Yeah, say, what's going to happen when you bring them closer to each other? Mechanism shear is going to be higher, right? When you bring them, don't forget, here's the equation for the mechanism shear. Mechanism shear is going to be equal to the moment divided by the distance from the center of the RBS to the center of the RBS. So you bring the two plastic hinges close to each other, you're going to have higher mechanism shear. And look what's going to happen here at the moment at the face. Moment at the face is going to be equal to MPR. Now you push the plastic hinge to be inside, which means this cantilever length or S sub H is going to be going up. And you're going to have a hard time to make this work. So you'd like to set the plastic hinges away from each other as much as you can. This is going to be your target, right? You try to minimize this A as much as you can, right? How about B? You can say, yeah, try to make it smaller, because when you make it smaller, you put the plastic hinge in this direction. How about C? You say C, try to maximize it. So there's certain elements that you'd like to maximize and certain elements that you'd like to reduce to control your design. Any questions? Hey, it's time to wake up.
So the easiest thing to do would be increase L prime.
As
That
much
way
as you can, yes. And the reason that, and the way that you do it, you're going to be reducing A as much as you can.
Wonderful.
When you reduce it, you set them away from each other. All right, you guys have a good night, and please sign out. See you next time.
Hey, good night, Professor.
Yes. Good night.
Are we going to be doing the same thing where we do the individual talk to figure out what our test grades were?
What do you mean? You mean for the meeting?
Yeah, are we doing the same type of meeting thing to get our test grades?
I'm not sure if you have seen already the